So this is my section 5.4 practice problem 199 video log. The first thing I'm going to start by going over is what section 5.4 entails, what are the most important concepts. This pretty much is the section where we start bringing in the comparison tests, where we try to find a second function that is very similar to the first series, and by comparing how those series are related, like whether the second series is bigger or smaller in its growth, we are able to calculate the convergence or divergence of both of those series. And this is done by, the first one is just called a comparison test. You are given a series a sub n, and you don't really take an integral or anything. You try to find a similar function that you know, like the growth rate to. So like if it's like 1 over n minus a fourth, that is very close to just 1 over n. Like the one difference is just the minus 1/4. So you can use 1 over n as your comparison, knowing that the original series will just be a little bit bigger than it. Yeah, will be a little bit bigger than the 1 over n function, because the denominator will actually be smaller since it is subtracting that minus 1/2. So if we can find whether 1 over n converges, like by using a p-series test, then you can determine that the original function also converges by using the comparison test. So the rules for the comparison test are initially that if you have two series a sub n and b sub n, and b sub n is greater or equal to a sub n, which is greater than or equal to 0, and all of that converges, like if b sub n converges, then a sub n also converges. But if a sub n is greater than or equal to b sub n, and that's greater than or equal to 0, and b sub n diverges, a sub n diverges as well. So the converse of these statements are, of course, true as well, but that is just the base of what a comparison test is, just finding an approximate function and then determining its relationship of growth and determining its convergence from there using a p-series test per se, p-series test, limit comparison test, which is what I'm about to go in next, integral test, whatever you want to test whether it converges or diverges. The limit comparison test, however, it works in a similar way. You find a comparable b sub n function that you may take the limit for, actually. So what you're doing is you are given an original function, you find a second function that is a close approximate, and you determine its growth, you determine its relationship. And once you do know the relationship of the first series a sub n to the relationship of b sub n, considering that a sub n will be bigger than b sub n, we can take the limit of a sub n over b sub n, and if that does not equal 0, then both series either converge or diverge. The limit comparison tests, it's a pretty good way of determining the divergence and the divergence of the original and final series pretty quickly. The conditions are pretty simple in the sense that once you try to create that limit, you putting the first function over the second function. If it is 0 and both of them are bounded, they do converge. If it is approaching infinity and it's unbounded, then they both will diverge. And I guess the simplest way to say it is you make sure you have three components, that a sub n, that b sub n, and the n value where it has to be past the first initial point of the series. Like it has to be like the first, it has to be like at least the first element in the series. But all you do is you take the limit as n goes to infinity of a sub n over b sub n, and if the limit does not equal 0, then both the series both converge or they both diverge. But if that limit equals 0, then b sub n and a sub n definitely converge. If it approaches infinity, then they both diverge. And that is essentially the two biggest and I guess like the only things in this chapter that you should retain moving forward, because those again just add on to the list of tests that we can conduct on a series to determine its convergence or divergence. Again, it's just another method that we can choose from depending on the form that a given series is in. So I chose question 199. That was also from the practice problem set that I did not, one of the questions that I did not get around to the first time. And this question is the series summation as from n equals 1 to infinity of n factorial over n plus 2 factorial. So just to show you the equation, where we're going from here is we're going to define that a sub n equals n factorial all over n plus 2 factorial, and then I actually remember this is one of the things that I factored in one of the past questions, n factorial over n plus 2 factorial. Yes, from question 3 in section 5.1. So pretty much n factorial over n plus 2 factorial, the n plus 2 factorial can be taken out and written as n plus 1 times n plus 2 times n factorial. Because again, if you think about it, it's just like say n is 3, n plus 2 is just 5 factorial, and if you put 3 factorial and then 5 factorial on the bottom, the 3, 2, 1, like the 3, 2, 1 factorial cancels out, and you're just left with 5 times 4, which is just n plus 1 times n plus 2. So we can cancel out that factorial of n factorial, and we just arrive at 1 over n plus 1 times n plus 2. So this is actually a lot easier to work with. I'm just going to show you the work. This is a lot easier to work with because the function that I'm going to choose to compare this with is just 1 over n squared. Because again, like if you just factor this out, it will be n squared plus 3n plus 3. So at the end of the day, like this function will be smaller, like the original a sub n function. A sub n function will be it will be smaller than 1 over n squared, because again, when you FOIL this out, it does have other terms other than n squared, so therefore the denominator decreases more rapidly than that of the 1 over n squared function, and therefore the 1 over n squared function will be just slightly larger. And what we can do for this is, it's actually really convenient. Like the 1 over n squared can just be rewritten as 1 over x squared, and we can do the p-series test on it. And since it's already in that form where p equals 2 right now, p equals 2, which is greater than 1, and if that p-value, again, if you remember the rules from the p-series test, since that p-value is greater than 1, it does indicate that it is converging, and therefore both a sub n, which is the series, which is a sub n equals the series from n1 to infinity of n factorial over n plus 2 factorial, and b sub n, which is the summation of n equals 1 to infinity of 1 over n squared, both converge due to p-series test. Okay, so this one was actually not too difficult either. If you remember the rules of kind of how to simplify down the operand, like the numerator and denominator, it helps you get a closer approximate, and it just was a lot easier to deal with 1 over n squared to find the convergence than that original function, because again, they both grow at a comparable rate, which is why we can use the comparison test. And I could have used the limit test, but since it was already in the form 1 over x to the p, and we had a p-value that was greater than 1, that was just the easiest and probably the smoothest way to solve this question. But again, the limit test is just as useful to like finding the convergence or divergence of both an and bn. All you need to do is, again, we need to find the comparable function of bn, and then from there, if we just take the limit over the function and then we evaluate the limit and we find whether or not it is equal to 0, whether it's approaching infinity, or whether it's not equal to 0, it can only be either one of those three options, then we can determine the convergence of the series a sub n and b sub n. So the limit comparison test could have also been used, but the p-series test was the more advantageous choice for this example, at least. And that pretty much sums up section 5.4. It was just along the lines of the same thing as all of chapter 5, where we're just trying to determine which comparison test to use in which scenario when determining if a equation or series is converging or diverging. Thank you.